Good morning. Welcome to the webinar series on managing drought in the Southern Plains. I'm Mark Schaefer of the Southern Climate Impacts Planning Program. I'll be the moderator for today's webinar. Margaret Boone, SCIP Program Manager, is back with us as managing the webinar. I want to thank Rachel Riley for running these webinars while Margaret was on maternity leave. Congratulations, Margaret. This week's presentation topic is groundwater, surface water, and recovery from drought. Presenters include Bob Puls, Director of the Oklahoma Water Survey, Larry French, Director of Groundwater Resources at the Texas Water Development Board, Eric Jones, Development and Operations Hydrologist at the National Weather Service, Arkansas Red Basin River Forecast Center. That's a long name to put on a business card. And Duane Smith, Water Consultant for the Choctaw and Chickasaw Nations and former Director of the Oklahoma Water Resources Board. Presentations will look at how underlying soils and aquifers must be recharged in order to sustain surface water resources, and how we can monitor and model these water sources so that we cannot see. As always, the webinar will feature an update and outlook on the region's drought conditions from Brian Fuchs, climatologist at the National Drought Mitigation Center, and comments from the region's state climatologists. I know that we have Dave Dubois from New Mexico and John Nielsen Gammon from Texas are on the call with us today. So as you go along, if you have questions for them, they'd be happy to take them. I would like to recognize the support of those who made this webinar series possible. Chad McNutt with the National Integrated Drought Information System, Mike Hayes with the National Drought Mitigation Center, Dave Brown with NOAA's Regional Climate Services, and the SCIP and CLIMAS NOAA RISA teams. We also greatly appreciate those of you who join us in the webinar series and recognize the valuable time that you commit to participating. You'll notice a poll come up on your screen. At each webinar, we provide an opportunity for you to tell us what topics are of most interest to you. We use this information to line up topics and presenters and future webinars. Here we go. You can also let us know through the chat box or through emailing or calling SCIP. Our next webinar will be May 24th, which will be the shortened briefing version that we do. On the next full webinar with focus topic will be June 7th, with a topic to be determined from these poll results. So you'll now see several options, so please indicate what is most of interest to you. I'd also like to highlight a couple of meetings in our region that are coming up that may be of interest to some of you. The Academy of Medicine, Engineering, and Science of Texas will host the 2012 Texas Water Summit in Austin on May 20th to 21st. The summit will look at current and future challenges and technologies to assure enough clean water for Texans despite an uncertain climate. The South Central Climate Science Center will continue its rollout meetings, with one hosted in the Houston-Galveston area on June 12th. Additional local meetings are being planned. These meetings are designed to collect guidance from people such as you to help define research needs for the region. If you know of any meetings that would be of interest to this group, please let us know so that we can include them in future announcements. We'll move on to another program I'd like to make sure everyone is aware of is the CocoRAS program. CocoRAS is a national network of volunteer observers who record rainfall, snowfall, and hail each day. There are currently 1,878 active observers in Texas, Oklahoma, and New Mexico. The reports provide a high-density network that supplements many of the other observation technologies you've seen on these webinars. Most importantly, it can provide detailed, localized look at rainfall patterns that can help fine-tune drought assessment as well as managing heavy rainfall and snowfall events. All you need is a rain gauge to participate. Contact CocoRAS or your state climatologist for information on how to join. Lastly, we'd like your opinion on whether it is still necessary to continue the shortened fourth Thursday briefings. We've noticed a lot fewer participants on these briefings and wonder if an update every 2 weeks is still necessary, or if the regular monthly webinar would be sufficient. If it is important enough to continue, we will gladly continue doing them. If the more frequent briefings are important to only a few people, we may be able to make accommodations for those needs and lessen the production demands on our partners. Of course, if we do cut back, we can always increase the frequency later if conditions begin changing rapidly again. So if you could please indicate on the poll whether it's something that you use in operational decisions and really rely on that second briefing, or if it's just more background, please let us know. As always, you may ask questions or make comments at any time through typing in your chat box. We will address questions at the end of the presentations. We'll put up a list of resources at the end as well that will help you find some additional information. I will now turn it over to Brian for an update on drought conditions and outlooks. Brian?
All right. Good morning, everyone. Again, I'm Brian Fuchs. I'm a climatologist with the National Drought Mitigation Center in Lincoln, Nebraska, and also one of the U.S. Drought Monitor authors. And I'm going to take you through the update and short-term outlook, as well as a couple quick highlights on some products that you may or may not be available. So next slide. Here is today's U.S. Drought Monitor. And looking at the country as a whole, you can kind of see this division between north and south. And realistically, the central and southern Rockies through the southwest and into portions of New Mexico and West Texas have really been the areas that have seen drought development over the last several months and continuing as far as parts of West Texas, but not today, which we'll get to a little bit later. And then that area down in the southeast from the Carolinas and Alabama into Georgia and northern Florida, this area has been hanging on now for a good part of a year to about 15 months in places. And right now it does not look like too much in the next few weeks to months as far as any improvements in this region. Next slide is a regional view. And not too much for changes this week. We did see a lessening in some of the intensity, especially on the D4 drought compared to where we were last week, where only about 3.72% of the region is now on D4, and looking at D3, only about 15.33% of the region. The number that sticks out is where we were a year ago. We were just really ramping up the drought, and we had about half of the region in D3 or D4 drought at that point at the beginning of May last year. So we have continued to see steady improvement, and we are hoping that this continues. And we have seen some of that continuing with the rain that is falling today and the outlook as well. Next slide. Just wanted to highlight some of the more recent conditions that we've seen, and really a tale of two different sides of drought here, with both short-term improvement and then some longer-term deficits that are still hanging on. So you look at these maps here from the ACES systems from the regional climate centers and the 30-day departure from normal, and we can see some areas that over the last 30 days, this time of year, we see some fairly high monthly totals. And we were below normal through a lot of the region, looking in parts of Oklahoma and West Texas where they were above normal as far as their departures over the last 30 days, and taking that out to 90 days. And you can really see the areas that have had quite a bit of improvement over the last 3 months, and the very wet conditions over East Texas and into Louisiana, as well as in northern Oklahoma and southeast Kansas. Next slide. Year to date on the upper right, really can see that improvement that we've been talking about, and how we've been making these improvements on the drought monitor. Is much of Texas, Oklahoma, Kansas, Louisiana, even in Arkansas, have seen anywhere from 3 to 6 inches above normal precipitation for the calendar year, and that even extends back into the fall if we would look at the water year. And we go back over the last 12 months, and that's where things start to change in that lower left-hand panel. You can still see, and I've highlighted a couple areas where these departures over the last 12 months are still anywhere from 12 to 16 inches, even approaching 20 inches along the Gulf Coast of Texas. And so even with the short-term relief that we've seen to the drought conditions, there are still some lingering problems, and the idea is that each area is going to recover differently from these, and how long does that short-term improvement take away from that long-term memory of a region. Going into the summer months, that's always going to be key, is what is our temperatures going to look like this summer, as well as how are we going to respond in these regions if we do see the precipitation shut off. How quickly will we see deterioration in some of these areas that are very vulnerable from the drought of the last year and a half. So just keep that in mind. Next slide. Again, this is looking at that short-term improvement versus long-term drought issue. You look at the 12-month SPI, and you can almost draw a line starting in central Oklahoma through central Texas, and excluding some of that area along the Gulf Coast of Texas, where I just highlighted some of those deficits, but you have seen quite a bit of improvement over the last 12 months. We do see some SPIs that are still running -1.5 to even 2.5 to -3 out in West Texas. And the 24-month SPI in the lower left is showing that this definitely is a longer-term signal at this point, that the short-term relief and that longer-term dryness is still what we're trying to figure out, and how quickly we can show some improvements in these areas when they do receive rain, that there's still quite a bit of deficit that we're making up. And again, I mentioned earlier that each area is going to respond differently to their vulnerability of just how quickly they can respond and show improvement to their drought situation when the rains are taking place. And looking at what's going on across much of Texas today, we have seen, again, this more regular rainfall pattern continue, a nice slow rain event that we should get a lot of infiltration. So that is going to definitely, again, help to improve the situation, and hopefully we can show some lessening of the intensity again next week on the map. Next slide. Here's the 5-day outlook from HPC. Again, looking at the lower left-hand panel first, definitely seeing this widespread rain event all the way from central New Mexico into much of Texas. And this is definitely falling on some of the areas that need it. The long-term drought areas, anywhere from 2.5 to 3 inches of rain in central Texas, 1.5 inches out in central New Mexico, and even greater amounts along those Gulf Coast regions and into East Texas. So as we watch this system continue to develop and this slow-moving, very, very good beneficial rainfall, as I would call it, continue, we can continue to see more positives in this region than negatives. Looking at the temperature outlook, definitely with this area receiving the rainfall over the next 5 days, you can expect temperatures to be below normal, which we're seeing, and through much of the central and southern plains, as well as the Gulf Coast and southeast regions. Quite a bit of heat out in western U.S. That's not helping their conditions at all out there, especially where we've seen that the early snow melt taking place, and some areas have already melted out, which is setting records in many locations for how quickly the snowpack has diminished this year. So something to keep in mind for our neighbors just to the west. Next slide. The 8 to 14-day outlook, we'll start with the temperature in the upper right-hand column. Again, the area of the central and southern plains where most of this precipitation is falling over the next 5 days is actually extending into the longer term, where temperatures are going to be looking at pretty much near normal during that whole 2-week outlook period, even some below normal out in Florida as this system moves further to the east. The above normal probabilities are taking over most of the rest of the country and even up into Alaska. The probability for precipitation on the lower left-hand panel, we continue to see the plain states showing above normal tendencies for this time of year, as well as the southeast, which some of those drought areas definitely could use that at this point in time. But that dryness over the west and returning everywhere from the Great Lakes down into Texas does remain in this outlook. So hopefully this event that we're seeing taking place now and over the next several days continues to materialize and bring what has been progged through the models, as it looks like in the extended, it looks to be a little bit drier during this time frame. Next slide. And here's the seasonal outlook here from the Climate Prediction Center, looking at May with temperatures and pretty much the probability of above normal temperatures through a great deal of the country outside of the West Coast, and also precipitation, especially over the Great Basin, looks to be below. The probabilities are for below normal precipitation and equal chances through a lot of the country. So not a lot of help or guidance with that forecast. And for the seasonal, more of the same. We're looking at temperatures to be well above normal all the way through much of the Great Basin and Southwest, the Southern Plains, and up until the Gulf Coast and Mid-Atlantic states, and equal chances for most of the country on precipitation, but we do see a below normal tendency starting to show up over the Northern Rockies into the Pacific Northwest. Next slide. The seasonal drought outlook came out last week, And again, we're going to focus on two parts of the country. The southeast we'll start with, and up into the mid-Atlantic and New England states. Some improvement taking place, still persistent drought over much of Georgia, South Carolina, and Alabama, where we see those conditions now. But it looks like there are some chances for improvement in some of the other areas of at least a category. In the southern plains, looks like areas along the Texas Panhandle and Oklahoma Panhandle look like some chances for some improvement, but we still see this persistence taking place through much of Texas, New Mexico, into Colorado, and even some development taking place in some areas. And that's really looking at this time frame of through mid-July. I think it's picking up on some of the vulnerability of the area that, a dry, not even necessarily dry, but a hot summer with a ramped up water demand taking place. Some of these areas are not going to have the opportunity, even with normal rainfall, to show much more improvement going forward. So we definitely are welcoming the rain events that we're seeing right now, and hopefully they can continue, especially over the shorter term, as we experienced quite a bit of heat last summer, especially wind was a problem where we saw ET values rapidly increasing through much of the Southern Plains region. Next slide. Just a couple products I'm going to highlight here on the What's New section. And these are products that help monitor soil moisture and groundwater conditions. Three individual products I'm going to look at quickly and provide informational links for you. Is on the lower left, the GRACE-based groundwater storage that's being done by NASA. The VIC soil moisture products that are being done out at the University of Washington, and then some of the work being done by the NLDAS group will be highlighted as well. So next slide. The GRACE data simulation, I'm not going to read through everything on this slide because they will be posted. I do have the link, and what we're looking at here as far as the GRACE groundwater storage product, we have a root zone soil moisture product, and we have a subsoil-based soil moisture product. These are being housed here at the NDMC, but they're being put together by NASA with their GRACE satellite suite. These are fairly new, and we have been using them quite a bit since they came out, just as another tool as far as drought monitoring and water storage. Next slide. The University of Washington products using the VIC model. They have I gave a paid link to their homepage. These are based off the VIC model, but they do show some others as well. And there's everything from drought monitoring to runoff to snow water equivalent and other products that you can get from here. Basically looking at how infiltration will be taking place and how those soils will respond in different parts of the country based off of not only climatology but also current conditions and precipitation. And my last slide is this NLDAS, which is the North American Land Data Assimilation System. And this is coming out quite regularly now. There has been some hiccups in the system, but there's different products to look at, both root zone and total water or soil column moisture. There's a stream flow product, and there's also an evaporation product on here as well. So it can really help those who are interested in not only water demand but infiltration and how that water is making its way into the hydrologic system. And this is through an LDAS. And I think my next slide is my informational slide. Yep. Here's my contact information, my email and phone number. If you have questions and want to contact me offline, please do. I'd be glad to answer those. Thank you. And Mark, I'll let you announce the next speaker.
Okay, thank you, Brian. We're now going to move into the kind of the focused topic, which will be on the groundwater surface water interactions. We're going to start off with Bob Puls, who's going to kind of give us a little basic hydrology lesson about how all this, how the water gets from the top to the bottom, and we'll take it from there. Bob.
Hello, everybody. I'm the director of the Oklahoma Water Survey. This is an organization that just got started here at the University of Oklahoma in January. So one of the challenges for Oklahoma and for this, and one of the objectives for the survey is the realization that increasing demands for sources of water combined with changing land use, population growth, aging infrastructure, climate change, all these things pose significant threats to our state's water resources. And in order to address those threats, we need to manage the state's waters in an integrated, sustainable manner. And by doing that, we can limit, if we don't do that, we will limit economic prosperity and jeopardize both human and aquatic ecosystem health. Next slide. Groundwater is often taken for granted because of the out of sight, out of mind mentality. Actually, I spent the last 25 years of my career working at the Robert S. Kerr Lab in Ada, Oklahoma, where groundwater was our major focus. It's important that we understand the connections that exist between ground and surface water as part of the hydrologic cycle in order to successfully manage those water resources. Next slide. The short message is that it's all connected. There's constant exchange of water in and out of stream bed and banks between groundwater and surface water. Gaining streams are streams that are being recharged by adjacent groundwater. This is where the water table is actually in contact with the stream. Losing streams that are actually recharging the groundwater. And so we have exchanges across these interfaces, and this can affect not only water quantity assessments, but also can affect water quality, depending on where contaminants are coming from, whether they're coming from the groundwater or whether they're coming from surface water. Both sources can be exposed. Next slide. This is just a cartoon looking at an example of a losing stream where the water is moving out of the stream into a sandy gravel aquifer. What I want to note here is that aquifers vary considerably, and I think you'll hear more about this in some of the succeeding talks. So we have very gravelly aquifers. They have very high yields. When you pump those aquifers, they're very prolific in producing waters. Fractured bedrock, on the other hand, has very low yield. But basically all subsurface systems have water in them. Even shales, where we are recovering gas and oil from these days, have water. They just hold that water more tightly. Next slide. In terms of understanding whether a stream is gaining or losing with respect to the contact with the groundwater temperature, sediment temperature is often used. It's very simple. It's a simple tool, but it's fairly accurate because the temperature will be fairly constant in those sediments in a gaining stream. In a losing stream, you're going to see temperature vary with the temperature of the water. So it's a very cheap, inexpensive way of identifying it. And the same reach of a stream can be gaining or losing depending on the time of year and what's going on in terms of rainfall, precipitation, runoff, and so forth. Next slide. You can also have what's called disconnected streams. Essentially, there is no contact between the groundwater and the bottom of the stream. So there's this vadose or unsaturated zone that exists between the stream and the groundwater. There is still movement, however, of water down to the groundwater, albeit much slower. And this is an important component of aquifer recharge. And then there's bank storage. This is when a huge flux of water comes through the stream, and this could be caused by a large storm event, rapid snow melt, or release of water from a reservoir. When this happens, the adjoining banks get charged with water. In terms of groundwater surface water interaction, there's also this issue of scale, both temporal and spatial. So watershed scale groundwater surface interaction can be on the order of miles. And here we're typically talking about entire watersheds supplying stream base flows. Then you could have near stream groundwater surface interaction. This is on the order of feet and days. Captures the losing, gaining reaches of streams that support aquatic and riparian habitats. This also gets at the issue of the age of water. So as you move down below the Earth's surface and go progressively deeper, you're going to encounter water that is of differing ages, from years to decades to centuries and even longer, depending on the depth of that water and recharge patterns. Skip that. And then finally, there's sediment scale groundwater surface interaction. This is on the order of inches and minutes. And what we're talking about here is groundwater surface water interactions across the stream bed and groundwater zone. And this is referred to as the hyporheic flow or the hyporheic zone. Next slide. And this particular zone is critical in support of aquatic life. It's also important in terms of regulation of contaminant transport in subsurface systems, whether that transport is moving from groundwater to surface water or from the surface water into the groundwater. Next slide. The extent of that zone depends on the three-dimensional characteristics of the stream. So it depends not only on the depth of the stream body itself, but whether that stream is a meandering stream, which would increase the lateral distance of the hyporheic zone. Depends on the elevation of the stream body in terms of whether there's pools and riffles and falls. That'll affect the depth of the hyporheic zone. So it's really a three-dimensional zone that one needs to think about. The other thing, perhaps the most important characteristics of this zone, is that there exist extreme variations in oxygen levels, characteristics of microbial processes that are going on in that zone, and the speciation of inorganic compounds such as nitrogen, iron, and other species. So this can affect, as I said earlier, the transport of species between surface water bodies and groundwater bodies. And basically having a healthy hyporheic zone, for instance, in the case of nitrogen, can really have a positive impact on the attenuation of nitrate in our systems. So it is an important source of nutrient uptake by microbial processes for aquatic organisms. It's important in terms of the absorption and precipitation reactions that occur in that zone that are driven by the redox characteristics of that zone. And then the issue of pumping wells. Wells can divert water, discharging to adjoining streams, and increased pumping can draw essentially all that water away from the streams, resulting in reduced flows and negative impacts to aquatic organisms. This gets at the issue of sustainable environmental flows in our streams. So this particular impact, that is pumping wells, can overwhelm the capacity of aquifers and streams, depending on the hydrogeologic characteristics of both the streams and the aquifer system. And I think that's it.
All right, thank you. Thank you, Bob. We're going to go now to Larry French with the Texas Water Development Board. He's going to tell us a little bit about how this all gets put into practice and some of the different characteristics of aquifers that they're dealing with. So, Larry?
Good, thank you very much. This is Larry French with the Texas Water Development Board. So I'm going to talk a bit about groundwater recharge and then try to relate that to what happens in drought conditions and look at a couple of examples of two aquifers in our state. Next slide. So this is an outline. Basically, we'll talk about what recharge is, how it's measured briefly, then talk about a couple of aquifers, and then talk about some groundwater management issues. Next slide. So first, what is recharge? How do we measure it? Next slide. So recharge, basically, looking at this cartoon schematic cross-section of a generic aquifer, Recharge is basically the blue arrow. It's simply the water that's infiltrating to the water table of an aquifer. But as you can imagine, the real world's a whole lot more complicated than this picture. And recharge is affected by a lot of things. Obviously, drought directly affects and reduces the amount of water that's available for recharge. But when we look at a couple of examples, we'll see the different kinds of aquifers can experience relatively little impact or very direct impact from a drought. Next slide. So how do we measure recharge? Really, I prefer the word estimated. There are various field techniques, other approaches to measure it. There's a lot of variables that, and the recharge isn't directly measured in most cases because there's just a lot of uncertainty and variability that exists. One thing to consider about recharge is whether you're talking about diffuse or focused recharge. Diffuse recharge involves general downward movement of water over a wide area, which was kind of like that cartoon we just looked at. But recharge can also be focused. Really, that is, superficial features can direct and concentrate water into a limited area, and that can result in an uneven distribution of recharge. So you think of situations, it was like presented just in the last presentation, which streams or lakes intersect the water table, and that can provide a preferential route for water to enter the subsurface. So we'll look at focus recharge a little bit later in the presentation. Finally, there are a lot of different techniques for looking at recharge, and it depends what part of the subsurface or surface you're looking at. Next slide. This slide violates all the good PowerPoint practices, but I wanted to show it anyway because there's an excellent survey of recharge conditions that's been done for the state of Texas. Bridget Scanlon, who works at the Bureau of Economic Geology, has done a good deal of work in this area. What she's done is summarize the various kinds of techniques that can be used to quantify recharge. So it depends on your aquifer situation. That's labeled on the top row there. So there's a variety of approaches that can be used. So for surface water, you may be looking at a base flow discharge of streams, modeling of discharge, a water budget approach. For unsaturated zone modeling, that's another approach that's not straightforward, but it's been used. Saturated zone water table fluctuations, and then tracers such as chloride or various isotopes. So basically what I'm trying to get across here is that quantifying recharge isn't straightforward, and it really requires a good knowledge of the aquifer condition, the soil type, and other factors you're looking at. Next slide. So now we'll just move on to a couple of examples. Next slide. The Oglala is one example we're going to use, and we're going to look at the Edwards as the other. Of course, the Ogallala has been studied for years because it's a critically important water supply source. I've looked up in literature values, and the recharge varies from pretty low, almost nil, from 4/1000ths of an inch to nearly 2 inches a year in upland areas that aren't being irrigated, and that would be an example of diffuse recharge, to much higher levels, maybe half an inch or over 8 inches a year in these playas, which are lakes that receive a lot of drainage. So you have a variable condition there. In the Edwards Aquifer, which we'll talk about in a little bit, of central and south Texas, it's a completely different kind of aquifer. It's a karstic aquifer. Recharge is dominantly through the infiltration of surface water. It's a very dynamic system and highly variable. Next slide. So this is, I actually like the previous slides, the other presentation earlier were much prettier, but this basically shows some of the fundamentals of how different recharge conditions exist. The top cube, you could say, represents conditions of the Ogallala, which is mostly sand, gravel, silt. Groundwater movement is through the pore spaces. The water moves slowly downward through 10, sometimes more than 100 feet of unsaturated material. But flow in the Edwards Aquifer, which is kind of like the bottom cube, has void spaces and conduits, fractures consistent with a karst aquifer. So surface water can readily enter the aquifer through fractures and voids, then move rapidly to the water table and travel actually tens of miles in a matter of days. So if you have the same rainfall event occurring on each of these different kind of aquifers, you're going to get a completely different response in the aquifer. Next slide. So let's look at the Oglala Aquifer in the high plains of Texas. Next slide. In the early days, groundwater was pretty easy to obtain and supplied water for irrigation systems. I just like old pictures, so this is a nice well yielding about 1,200 gallons per minute. Next slide. But years of doing that have resulted in declining water levels in the aquifer, and portions of the Oglala have experienced more than 150 feet of drawdown since development began. Really, the reason this is happening, of course, is that pumping has far exceeded the amount of water being recharged in the system. So let's look at how recharge is occurring. Next slide. Here's another cartoon showing a conceptual cross-section in the Ogallala centered on a playa. So very little recharge, very little water is recharged diffusely on the upland areas, which are shown on the margin of the slide. But focused recharge can occur under the playa, which is receiving runoff from nearby areas. So while the drought may not immediately affect the aquifer where it's receiving diffuse recharge, because those rates are pretty slow and the movement is slow, there may be a greater effect if the playas are dry or wet for extended periods. So really how much drought would directly impact the Oglala isn't well quantified, but probably the biggest impact of drought on an aquifer such as the Oglala is just the extension and prolonging of a pumping season because of the lack of rainfall. So this kind of situation contrasts sharply with the Edwards. Next slide. I mentioned earlier the Edwards Aquifer is a limestone karst aquifer. It's fractured and faulted and occurs in an arc around central and south Texas, kind of centered in the San Antonio area. And it serves as a drinking water source, actually sole source for San Antonio and other areas. Next slide. This is a cross-section that goes from the northwest to the southeast through the Edwards Aquifer area. The Edwards itself is the lightest colored unit on either side of the slide. So surface water runoff flows from the upland areas on the left, creeks and rivers, and then when it flows over the fractured and faulted areas of the Edwards-Conix Fault Zone on the right, that's when you get infiltration into the Edwards Aquifer. Next slide. This is one of my favorite pictures and pretty much tells it all. What happens over the Edwards Aquifer when you have stream flow. As you can see, you can get very direct and rapid focused recharge into the aquifer. And this kind of backs up what I said earlier about this recharge being highly variable and dynamic. Next slide. So San Antonio has been very concerned about monitoring drought conditions and the groundwater levels in the Edwards Aquifer. They're very dependent upon surface water runoff, as you saw from the last slide. So drought is a very serious thing for the Edwards because it has a very direct and immediate impact. This slide just gives some information about San Antonio's groundwater monitoring program. They have a well-calibrated system where they understand as the aquifer levels drop, they have trigger levels which initiate certain steps to conserve water. The next slide. This is another picture of the San Antonio system. There's a particular index well, the J17 in San Antonio. And here you see a situation that is not like the Ogallala, which has a very kind of steady long-term decline due to pumping and limited recharge. So here pumping occurs, but the recharge is rapid. So you really get a picture of the drought conditions as there's a lack of or great reduction in the amount of surface water input to the system. Next slide. I'll just wrap up on this last topic of groundwater management issues. Next slide. So our sister agency, the Texas Commission on Environmental Quality, looks at public water supply systems, and quite a few of them are dependent upon groundwater. This is a monthly picture of the systems that are threatened by drought. This is just a couple of months ago, back in January. Notice that a lot of these systems are really in the central part of the state where we were just talking about, and they're dependent upon the Edwards Aquifer, so they're directly affected by the drought, lack of recharge. But you'll see also, even where the drought is more severe up in the high plains of West Texas, there aren't as many because the drought doesn't immediately affect the aquifer system like it does in the central part of the state. Okay, next slide. One system that was affected near Austin was the Spicewood Beach community west of our city. This public water supply system was dependent upon groundwater, but it ran out of water a few months ago. The groundwater wells are screened in alluvial or river deposit material, which those low levels in the wells were dropping as the adjacent lake level was dropping due to lack of surface water input. Other wells in the area were screened in non-alluvial aquifers. They had lower levels, but they weren't being dewatered. And really, the community didn't fully realize that they were essentially dependent on lake water, even though it was delivered via groundwater wells. So kind of one of the lessons learned in this situation was that you need to understand your aquifer and how it gets its water. Next slide. And then finally, we also have a situation, a kind of a reverse situation, which groundwater can serve as a source or one of many sources to surface water. So this slide makes some general points about the decline of water levels in Lake Meredith near Amarillo. These are very preliminary. These are just estimates. There's a lot of factors that go into the decline of water levels in Lake Meredith. But it's clear, as you can see, there's a base flow of groundwater that contributes to the lake. And so it's clear that groundwater is certainly a component of the lake levels and affects the other sources of water as well. And that just bolsters the message that Bob Puls gave about a very connected surface water and groundwater world. Next slide, I think is my last. So feel free to contact me if you have any questions. Appreciate it.
All right, thanks, Larry. And it's good to see how the science that goes on gets connected into actually the decisions and operations that people have to do. I like the way this comes together. The other aspect of this is touched on a little bit some of the things Brian mentioned about some of the models out there. Eric Jones with the River Forecast Center up in Tulsa is going to tell us about some of the products that they're doing with modeling and some new experimental products that will help us get a better idea of what's under the ground. Eric?
Yeah, I'm just going to cover a little bit about some of the new graphics we've created over the last few months on the model that we run here daily. The next slide. The way we compute it is we use the Sacramento Soil Moisture Accounting Model. It's basically a rainfall runoff model. We use it mainly for runoff, but we decided maybe we had some information of how the soils are actually doing, and we're going to start putting that out for our users to see if maybe they can get some kind of use out of it. The soil moisture accounting model is a 4x4 kilometer model. It's based on the OHD distributed hydrologic model. We use this model for our flash flood guidance every day, and we also use it for some of our distributed model runoff, some of our forecasting, and some points for distributed modeling. It's based on 17 model parameters, so it's quite complicated. The model parameters that we use for a distributed model are based on soil type and land use. On the Sergo and StatsGo, either one, we can use either one of those. But the only thing currently we're using climatological potential evapotranspiration. We don't have real time as of yet, but we have plans that maybe we could start using it in the gridded version of it that we have to produce every day. Next slide. The inputs that go into it, we use hourly QPE rainfall from radar engaged computation. The model runs in an hourly time step. The upper layers are computed from the two parameters of the upper zone tension and the free water values, and the lower values are computed via three different parameters, the tension water and the primary and supplementary values. Those primary and supplementary values go into base flow contribution into our hydrographs, into our forecast and our forecast model. Next slide. We were hoping that users could get more use out of this, in that instead of showing the entire soil moisture column, it's broken up into two different layers, the upper layer and the lower layer. The upper zones are more useful, hopefully, to agricultural use, and the lower zones are more useful for hydrologic and groundwater use. Next slide. Some of the computations that have gone behind this are climate monthly statistics. It uses 16 years of model data from 1996 to 2011. The reason why we were sort of confined just to those years is we started doing our QPE rainfall statistics. It started back in 1995, so we started, that's why we're only confined from 96 to 2011. We would like to go back further than that, but we really can't at this point. The graphics that we produce are produced each day around noon, and they are produced via our new program, our modeling program that we have is the CHIPS program, and all the Weather Service River Forecast Center started using that within the last year. Next slide. This is our main page. This is our main page that we have on the web, and that the URL is at the bottom. And then you can see in the circle, that is the link to the experimental soil moisture graphics page. Next page. I want to go a little bit about some of the graphics. We have 6 different graphics that go behind this, and the 2 biggest ones are the anomalies, the upper zone and the lower zone. The upper zone anomaly is sensitive to short-term rainfall. It could change drastically from day to day, especially during large rainfall events. And this represents the first few inches of the soil. Next slide. And you can see the picture here. The reds are the drier than normal, and the greens are the wetter than normal. And you can see this is from earlier in the week. And there is some, you can see where it's back up in southeast Kansas, as where that large rainfall occurred last week. You can see that's above normal. And but the actual soil moisture itself could be still, you can see in northeast Oklahoma, the soil moisture probably is still moist, but compared to normal, it's starting to dry out or be normal, or it's starting to dry a little bit more. But the big thing that come away from all of these graphics is you got to use them all in tandem. One, it shows you exact what the moisture is compared to the maximums of our model parameters, and the anomalies are just what's compared to normal. Next slide. The lower zones, they could change very slowly over time. They're not extremely sensitive to one particular rainfall event in particular, but they takes multiple rainfall events to drastically start changing their values. And the parts, this is impacted, these are affected by the extent several feet down into the soil column. Next slide. And you can see here, this is the anomaly. This is their groundwater. This is based on groundwater and the hydrologic aspect of it. And you can see our western part of our area is much below normal. We've been very much, the rainfall, as Brian showed earlier, you know, is in a drought. So this clearly shows that on this anomaly pattern here. Next slide. One of the notes on the anomaly values are very much more sensitive over the climatologically dry areas. So over our western areas, which get a lot less rain, you'll see the anomalies change a little more rapidly than over our eastern part of our area. And also, if you have any inputs on the scaling that we have, we will accept those. We just created those scales, and just we would like to see a lot more user interaction into this to see how we can start changing our product. Next slide. The upper zone moisture values, like I said before, it takes the 2 upper zone model parameters and has those versus the maximum. So it actually is the percentage of full. That's the total moisture values, and I'll show you a couple of those slides here toward the end. And I said we also need input on these. Some of the legends on that, we put legends on there by agricultural impacts, and we would like to have some feedback on that. Next slide. And you can see here, you can see how percent full. You can see where we had those rainfall across southeast Kansas, northeast Oklahoma. You can see the upper zones are still quite full. They're more than 40% full at this time. This is from earlier part of the week. But you can see across our southern and southwestern part of our area where we haven't any good rainfall over the past couple of weeks. You can see that they are very dry, and you can see the legend down there. We try to put some kind of impacts on it. Like I said, we would like to have feedback to give to our users. But they sort of wanted to say, you know, this is a significant agrological impact, or we could just say that they're just starting to approach some impacts on that. Next slide. Our lower zones, as I said before, it's the 3 lower zone model parameters versus the maximum model parameters of those. And that's another thing we would like to have feedback on these as well. Next slide. And you can see here, the eastern part of our area is quite full. The groundwater is more saturated, the first few feet of the soil. And the hydrologic impact of those aren't impacted too much. But you go in the western part of our area, where we have a lot more drier soils, where the rainfall hasn't been that great over the last few months, you can see a much more impact. Next slide. And this is our webpage with all 6 graphics. The top 2 are the anomalies. The next 2, the middle 2, are the actual the fullness, both the upper zone and lower zones. And then the bottom 2, which are sort of cut off there, are actually the normals. So the anomalies are based on the combination of the percent fullness of the middle and the percent normals are the normals of the bottom. Next page. And that's all I had.
All right. Thank you, Eric. I think one thing he mentioned, they want feedback. This is, if you notice, he had experimental model on here. It's something that's in development, and they really want to make sure that it's useful to people. So please go to the website, take a look at that, and there's contact information on there, or contact information for Eric, and let them know what makes it more useful to you. So I really encourage you to follow up with that.
One other thing I wanted to say on top of that webpage that we have, it has a good explanation of what goes behind the graphics also.
All right. Well, thank you. And now on to the last of the 4 presenters is Duane Smith with the Choctaw and Chickasaw Nations in Oklahoma, and a particularly sensitive aquifer, Arbuckle Simpson, and how it's fared through these recent drought episodes. Duane?
Thank you, and it's actually D-U-A-N-E on the slide, not the other way. But that's not a problem here. I've been called worse. Next slide. These are the major groundwater aquifers in Oklahoma, and you can see there in south central Oklahoma is where the Arbuckle Simpson aquifer lies. Next slide. It's a very unique aquifer. I'd say very similar. A similar aquifer would be the Edwards Aquifer in Texas, where this is a limestone karst aquifer. A lot of controversy started in this aquifer about 10 years ago when several large landowners wanted to get permits from the Oklahoma Water Resources Board and pipe this water about 85 miles up to communities in central Oklahoma. And under Oklahoma state law at the time, very similar to Texas, there was no recognition of the interaction between groundwater and surface water. Groundwater is a private property right, surface water is public water, and they're administered differently. As a result of this controversy now, this is the only aquifer in Oklahoma from a state statutory standpoint that has conjunctive use management. And the important piece of this in all of the studies that have been done is to see how much groundwater can be pumped while we still protect the integrity of the springs and streams. Next slide. This is an attempt to show the communities that use water, all or in part, from the Arbuckle Simpson aquifer. Communities there total of about 150,000 people. These are the current regulated uses of water in the Arbuckle Simpson. Agriculture use is very small. It's mainly ranch land, so the agricultural use is typically cattle grazing and those types of things, not much irrigated agriculture. municipal use. The city of Ada is the biggest user. Then there's industrial, some small industrial use, and mining operations of the rock quarries along the western side of the aquifer are growing in nature. Next slide. This is a sole source aquifer as designated by EPA. There was a women's group about 25 years ago from Ada that put together a package and sent to EPA to have this aquifer designated as a sole source aquifer. Basically, what that means to EPA is that if there's federal funds used in projects there, they would have additional review to make sure that the water resources are protected. Recreation and tourism are a major part of the economy of the area. Several wildlife management areas, the Chickasaw National Recreation Area. This is a part of the Chickasaw Nation, and back in the early 1900s, the Chickasaw Nation actually put a deed to the federal government for the Chickasaw National Recreation Area. Turner Falls, as you drive up I-35, you go through the cuts of the Arbuckle-Simpson. This is really a slide to show, I think it goes back to the slides of the Ogallala and the Edwards Aquifer, very similar, to show that this is a karst formation, that water travels very rapidly through the aquifer, but it does not store much water within the rocks. And the upper right-hand slide is an example to show yield versus drawdown, and I'm having a hard time reading that. The storage coefficients in the Arbuckle-Simpson are very small, and so we have much larger drawdown versus yield in the Arbuckle-Simpson aquifer than we would have as an example in the Oglala. The geology of the Arbuckle-Simpson and surrounding area, this is one that geology students love to go to and have field visits. Very unique, and a lot of studies have been done. The latest is a $6.5 million study that was funded by the Bureau of Reclamation to the Oklahoma Water Resources Board. And I would probably venture to say that more studies needed to be done to particularly understand the characteristics of the aquifer. Typical cross-section, it just shows rapidly how water will go down cracks and crevices into the formation and move then horizontally and vertically at very rapid speeds. It also provides the basic base flow for the streams and springs that then are used for public water supply, recreation, and tourism for the aquifer. Here's a list of the springs that flow from the Arbuckle-Simpson aquifer, and these are the major springs that have been mapped by the U.S. Geological Survey. And as a part of this study, then, the goal was to try to protect those springs and streams from groundwater pumpage. So what we've gained from that is that about 0.2 acre-feet per acre could be pumped from the aquifer and only reduce the springs and streams by about 25%. This is our 100-year hydrograph of the area, and one of the difficulties we've had, I think, throughout Oklahoma, but particularly in this area, is the last 25 to 30 years have really been the longest, wettest period in our history. We have all of our professional careers, the 80s and 90s, have been during a relatively wet period of time, and we see graphs of what happened in the 30s and the 50s and the 60s, but we didn't live through that time, and our people that live there are used to above normal precipitation. And when we have drought like we had last year, particularly, people tend to panic, and we try to educate people that that may not be even close to some of the droughts that we've had in the last 100 years. This is looking at water level lows in the aquifer, and when we look back at the worst droughts of records that we've had, we can see that during the drought of 2011, we've had very similar types of low flows in the springs and streams in the aquifer. This is the Blue River. This is a trout fishery that goes through the central part of the Arbuckle-Simpson Aquifer. And in 1956, which was our steepest drought of record, we had 28 consecutive days with no flow recorded. And then during 2011, we had 25 days of drought there that showed no flow recorded. So very similar drought periods for 1 year at least, and the steepest drought of record on the Blue River. The Chickasaw National Recreation Area, this is a slide to show what it looked like through that area. A high recreation area that people swim in the creeks and go there. And during the drought of 2011, this was the sign that was up to keep people out of the streams and creeks. These are the... I won't talk about this one. I was going to. So that's all I have.
Well, thank you, Duane, and also thanks to Brian, Bob, Larry, and Eric as well. They, I think you see the challenges of management and the way things used to be managed, about them being separate, considered separate resources, and what we've learned about how they're linked, and what more we need to learn, the challenges that are there. I hope that's a message we can take away and think about where the water's coming from, what we can't see and we can't measure very well, what we can do to try to get a grasp on that. So I know that there are several state climatologists. I know that John Nielsen Gammon in Texas and Dave Dubois is on the line, and I see that Mary Knapp from Kansas has been on the through the chat. So if there's any questions about drought status and things in those areas, I'd be happy to field those. I do see a question about that image that Duane had, the hydrograph. The legend on there, and this too, is in 2015. It's actually 2011. I don't think it's a prediction of what the flow is going to be in the Blue River. So, but I think showing the similarities to previous events that they've seen, haven't seen really those conditions in about 50 years. So, I guess there's, if there's any other questions or comments, please type them in the chat box, and we'll take those. This list of resources is a reminder for several ways that you can follow up with some of this. We posted presentation materials on the drought portal in the Southern Plains section, and we'll produce a 2-page PDF summary from this webinar and get that posted there and several other sites as well. The webinar recording will be posted to the SCIP YouTube page, so if there's others who weren't able to join us, please let them know that it's there. And also linked on the SCIP Facebook page. Our next webinar will be on May 24th, and that'll be the shortened briefing, and the next full webinar will be on June 7th. The focus topic will be determined based on the results of the poll here today and availability of presenters. As always, we encourage you to continue to spread the word to make sure that all those dealing with aspects of this drought are part of the larger community and can access support that they need. We encourage you to pass along the PDF summaries, webinar announcements, or any of the other information linked on these various sites. And I'd also like to mention that it's great that the drought has shown so much improvement, especially over the eastern part. I think some of the graphics there showing, you can almost see I-35 through Oklahoma and Texas, where the improvement has been. But reminded that it's still an ongoing event in the western part of the region, and into New Mexico, which is still something we're dealing with. So, so I hope that this information will continue to be useful to you. Thank you for your time today. We look forward to continuing this conversation with you in the future. I do see Mary Knapp is typing something right now, so see what she has to say. one last little bit, probably. But they did have those torrential rains in southeast Kansas, northern Oklahoma, and actually one of the lakes that Eric and group up in Tulsa has been dealing with is there's Lake Skytook there that just doesn't seem to want to fill again. It's been struggling, even though they've been getting abundant rainfall. So, well, I guess.
You know, Mark, I've noticed the reservoirs in Foss Reservoir and Alta Sluger, Fort Top have also been slow in filling. I guess when you look at their watershed area, it's still in severe drought, while the area where they're at is soil moisture.
Yeah, we that's one of the things that we monitor. I know John also in Texas and Dave, New Mexico. We all monitor reservoir information as best we can, and that is even with rainfall, we've been slow to show recovery there, partly because we don't see that runoff response showing up into the reservoirs. That a lot of it, figure that first rains, you have to recharge the upper soil moisture, then you fill farm ponds and everything. So it takes a few events before the rain gets there. But even more so than previous events, we see the kind of rainfall patterns and it's still not reaching the lake in substantial areas. And I know Altus especially is going to be struggling this year as out into the Panhandle. We've seen Lake Meredith and everything. But these reservoir aspects are one thing that we monitor. We're also noticing some signs of it starting to dry out a little bit in southeast Oklahoma. The short-term dryness that we've seen in the last month there is something we're watching closely. So we'd love to hear from people if you know places to get information or things that you notice. Please contact either Skip, Klimas, or State Climatologists. Happy to bring that into the Drought Monitor process as well. So, yeah, so I think, something we researched as well. Oh, Central Kansas is right. That's something we did focus on the rainfall in southeast Kansas, but a large part of Kansas has still been that kind of the western pattern. So most of the state, I think, is still struggling with that and still depicted in drought as well. So I think that's it, and I'd like to thank all of our presenters and look forward to you on the next webinar. Thank you very much. Have a great week.